Association and Science Teacher Association as a resource person for several years. Madam has contributed Madam has conducted teachers training for more than 25 years for the betterment of mathematics environment, and that is not the aim. Here again, you will be happy to know this, that she has been continuously guiding the students for mathematics Olympiad. Under her guidance, more than 200 students qualified RMO and more than 20 students qualified INMO. So, see, we are very much fortunate, such a experienced resource person we have here today.
Good morning, everyone. I, as you sir has introduced about Madam Komal, that she has a very vast experience of teaching Olympiad classes, and several students have qualified RMO. Many students have qualified INMO. Even she is associated with Mathematics Teachers Association as well as HBCSE, and now also she was busy taking classes from morning till night. Olympiad batches she is taking. So I think she is the most apt person for this kind of orientation program, and I'm very hopeful that you all will get the benefit of her experience and knowledge that she is going to share in today's two lectures. So, and I request you all that let this session be interactive. So that will be more beneficial. Yes, sir.
So very nice to see such enthusiastic crowd for mathematics. And first thing I need is that you should open up and helping your level and helping you well. So I've been told that you people have done our way, and now we are looking forward for RMO and INMO. Okay. So first, I hope. Yeah. Oh, yeah, sure. So I can move in this much.
No, we can see you.
Yeah. Yeah. So what I'll do is I'll start with the problem. Okay. And if you find problem very easy, you let me know. If you find problem very difficult, you let me know. So I can give you right level problem. Solving right level problem is very important because that will keep motivating you. Okay. So very first problem is, suppose I have a polygon. Let's say 100 sides, 100 sided polygon. And I have some points inside it, say P1, P2, so on, till P50. 50 points inside. Or let me take it 51 points inside. Such that out of these 100 plus 51, that's 100 vertices plus this 51 points. Okay, totally 151 points. Okay, out of this 151 points, no 3 are collinear. Okay, no 3 are collinear. Means neither 3 points from P are collinear, nor vertices are collinear, neither any two of these and P or any two P's and one P. No combination of 3 points are collinear. Suppose I want to divide it into triangles. I want to cut it into triangles. Cut it into triangles with all vertices as these 151 points. Then find the number of triangles. Okay? Further, find the number of triangles. Now here, there is one hinge. Okay? See, normally, does everybody know NPR, NCR? Is there anybody who doesn't know this? Is there anybody? See, when I say you don't know this, please reach out because see, these are Olympiad problems. Students will take time. So simultaneously, I can explain you also. Okay. So this is a chance for you to clear all your doubts. Okay. But only you have to open up because if I don't come to know, then I won't help. Yeah, I'll go fast. But not at the cost of understanding. Every child in my class should understand everything. Okay? So, everybody know what is N choose R? Huh? Okay? Huh? Out of N objects, we select R objects. How many ways are doing this?
N factorial by R factorial
N factorial upon
N minus R
wonderful. And what is NPR?
N factorial by N minus R.
Number of permutations. This is symbol. This symbol is symbol of number of permutations of R permutation. We say it means length R of N distinct objects. Okay. Followed? Everybody knows this. Now, gut feeling for this problem is when I say how many triangles will be there, I'm cutting it into triangles. Okay. When I say that I have 151 points and I need to form triangles, natural reaction to the students is it should be 151 choose 3, correct? Because every 3 points will give me one triangle. Okay, followed. So out of 151 points, okay, every 3 points will form a triangle. Correct? Okay. Now, is this the correct answer? But this is not the correct answer because I'll give you an example. Here I'm selecting all possible triangles. This is the number of possible triangles we can form. And here we have to cut the triangles. There's a difference. Why? This is a technique in solving any combinatorial or any number theoretic problem. Okay, this technique you note it down. Create a dummy small problem. Okay, so I'll create a dummy problem. Instead of 100 bond, I'll take a rectangle and I'll take 2 points like this. Okay, and let us see how many triangles we can cut it in. So suppose I label this A, B, C, D and this point as P and Q, and if I join them like this, okay, so how many triangles I'm getting right now? 6 triangles. Can I take one more cut like this? Am I allowed to do one more cut like this? No, why?
Because the other triangle is
Yes.
already removed.
Yes. This is extra vertex, which I'm not allowed. This vertex is not allowed. So I'm not allowed to cross the diagonals. Understood? Followed? Okay. I'm not allowed to give this cut. But when I count here such all triangles are counted. Everybody understood the difference between two? Any doubt, anybody? Here I can take any 3-letter triangle. Correct? Followed? So if I have to just draw triangles, there would have been 6 choose 3 triangles. Correct? Followed? But I have to cut triangles, then there are only 6 triangles. Okay? Because when I draw, I get many extra vertices, which are not allowed. Here, what my condition is, cut such that all vertices are from these 151 points. Okay? Is that clear? So, any clue, any hint, what could be done? Yes. What she is saying is same thing. Like you do this. Okay. One is creating a dummy problem. Second is it's a, it's a machine. We don't have control. Second is we can start one by one. Okay. So that's a very good idea. So let us start with one of the points. Let us call P1. Okay, very good. So let's start with P1. P1 gives me how many fragments? Suppose I have introduced only P1 here. Suppose I have introduced only P1 here. Then P1 will give me how many fragments?
100 C2.
With the vertices. 100 C to 100. Because P1 I can join every side will give me, correct? So P1 will give me 100 fragments. Very good idea. Okay. Now let us introduce second point P2. Right? Okay. I will introduce second point P2. So P2 now, where my P2 will lie? It will lie inside this. So if it lies somewhere here, okay, or other, it can lie on one of the side. Correct? Correct? Either it can lie in one of the triangle or it can lie in one of the side.
That's one of the side and we are not holding this.
Yes, we have already taken care of this. Can you see that? The question, while framing the question, they have already taken care of this. No three are calling. So this possibility is not there. Correct? But you need to mention it because RMO is subjective. Okay? So as no 3 points, is it okay if I don't write? You will be able to write. But you need to mention that statement. As no 3 points are going here, second point has to fall into one of the triangles. Now, how many triangles I will get because of this? One. Three. Okay. Somebody is saying 3. Somebody is saying 1. Okay. How many? Very good. I'm impressed. See, because clearly I know that I can't cross this, so can this type of line is impossible? No, there is big no for this type of lines. So I can cut along only 3. Suppose this is without loss, let us call it AB. I can cut along only 3 cuts. Which 3 cuts? We can give only 3 cuts. 3, oh, let me write here. 3 cuts possible. Which 3 cuts possible? P1, P2, P2A and P2B. So normal students will make this mistake that they will add 3 triangles. But you need to notice that my original triangle P1A, P2, or P1AB is lost here. Correct? It got cut into 3 triangles. So 3 triangles minus a triangle. So this will give me 2 triangles. Correct? Is that clear? Let's go to the third point. What will happen to the third point? Again, it will lie somewhere. It may lie here or it may lie in my new triangle, but it will lie inside some triangle. Right? And what it will do? It will again give me how many extra triangles? 2 extra triangles, correct? What can I say till P51? 2 extra triangles? Yes? So total number of triangles would be how many? 200. Perfect. Very good. Well done. This is a good class. Happy. Okay, I can do some next. Okay. So we have got the answer. This is what is called counting. Okay, so this is a counting problem. Now, is it possible to do this problem by some other method? Now let us introduce some very nice method. This was a very old IMO problem. I don't remember year, I'm sorry. Very old IMO. Now, but very, very old. Okay. That's why we find it very easy. Now, to let there be t number of triangles. When I cut, let I get t number of triangles. One thing I forgot. Do you by chance know the sum of angles, all angles of a polygon with n sides?
1 minus 2 is 180.
Very good. Everybody know? Is there anybody who doesn't know that I'll prove it? Everybody know? Wonderful. Very good. So what are we going to do is we are going to count angles. Okay? So here we have t triangles. So we have what will be the total angle sum of all the triangles formed here? Each triangle will contribute with some 180. And we can see that because we are cutting the triangles, their interiors are not overlapping. Correct? So total angle sum will be sum of all angles because no two triangles angle will overlap because their interiors are destroyed. As showing the total angle sum will be 180 t or pi t. Okay, if you I will choose 180. I don't know whether you're comfortable with that. 180 t. Okay. Now 180 t will be what? I have 100-sided polygon. What is sum of angles of 100 polygon? Sum of angles of polygon
98 and 180.
will be 180 into n minus 2. Correct? Okay. So this will be 98 into 180 plus. I have how many points? 51 points. What is sum of angle around each point? 360. So 360 into 51. Correct? Because I have 51 such points. Each point will contribute 360 degrees. What to do now? Solve. Solve. How? Divide first. Always try to make equation easy. Okay, divide. So what you will get t is equal to 98 plus 2 into 51. That is am I getting the same answer? Which method is better? Second. What I have done in second method? I have counted triangle without actually counting triangle. This is called combinatorics. Combinatorics is the art of counting without actual counting. Okay? Because in actual counting, what are demerits of actual counting is we may make some mistakes. For example, if I am not very conscious, I might write 3 here instead of 2. Okay? Though my idea and thought process is correct, some calculation error will lead to problem. But in combinatorics, it is an art of counting. And what we do in Olympiad, especially after RMO, of course, in RMO you need the counting problems also. Okay, you need counting techniques also. But post RMO, and even in RMO nowadays, they are more asking of combinatorial problems based on combinatorial. Now, we use one particular technique here. Let me introduce you to that technique. What we did, see, we counted same thing. What we counted? Sum of all angles. Total angle sum is counted. Okay? How we counted? We counted it by one method, which gives me LHS. Again, we counted it by another method, which gives me IHS. Okay? And these two will imply something. Correct? This technique is called double counting. This is very effective technique, double counting. What we do, we take same quantity, we count it in 2 different ways, and that mainly gives me some equations, or usually it is used to do combinatorial inequalities. This is very good technique, very effective technique for combinatorial inequalities, to prove inequalities. Okay? So So we'll see few problems on double count. Everybody has understood what is to be done? Huh? Okay. Now here, can somebody give me generalized formula? If instead of 100, if I have n points here and interior I have say m points, can somebody generalize the formula for me? Yes. So number of triangles will be n minus 2 plus 2 times n. Okay? Everybody understood this? Huh? Any doubt, anybody?
LHS square angle AP to B.
Huh?
That will include me wrong.
What's our inclusion for?
Angle AP
A,
B to B.
P to B. This, yes, of course. See, I have counted all angles around point P. Got it? So, in that, A, P to B will get it. This is included in these. Understood? We have added all angles around. समझ में आया? When we counted angles around these points, all these angles are included. So all these angles are included, and there are only two types of angles. One, angles with vertices as vertices of polygon, and secondly, angles with vertices as interior. Where there are only two types of vertices we have, either vertices of polygon or interior. Done? Huh? Now there is one. May I erase this? Sorry. Method 2, you want me to explain again? Okay, sure. What I'll do, I'll give another problem to people and then I'll explain. So that goes, suppose I have 2 minutes, I'll explain better. But I'll give one more problem so that those who are finished should not feel good. Okay, I have an 8 cross 8 chessboard. Now, everybody know chessboard puzzles. Okay? Now, if I take a piece of size exactly 2 squares on a chessboard, such a piece is called domino. Correct? Okay? And you people must have done that famous puzzle that if I cut 2 corners of the chessboard and give you 31 dominoes, okay, can you place it on the chessboard? Right? Okay. So, everybody is knowing that, then I will do some other problem. Yes. If you don't know, then try doing that. That is also a wonderful puzzle. Chessboard and domino. So, what I'll do is, here, I will color the chessboard. I have to color this chessboard with blue and red. I have to color this with blue and red such that each row and column has an odd number of blue squares. Okay? That is, see, mind it well, no restriction on diagonals. Only rows and columns. Which are my rows? Let me label this as R1, R2 till R8 and this as C1, C2 till C8. Okay? Rows are horizontal and columns are vertical. Everybody know this? Huh? Okay? See, in combinatorics you can label them the you want. Okay? You can start from base also. Okay? But here we are labeling it. Whatever you want to label, you need to mention. That's all. Okay? So, what is the question? I want to color it in such a way that each row and column has odd number of blues. Okay? One such coloring I can give you is that you color only diagonal cells. Correct? Then every row has one blue and every column has one blue. Correct? Or you can go along other diagonal, or I can color it in such a way that I will color these 7 blue and these 7 blue. So all these rows has one blue and last row has 7 blue. Here this column has 7 blue and all these columns have one blue. Right? These are some easy ways of coloring it. There are many more ways you can come up, create it randomly also you can color. Okay. Question is, find the number of such good colorings. Find the number of good colorings. Okay? Understood? What do you mean by good colorings? Good colorings means each row has odd number of blues, each column has odd number of blues. Okay? So in the problem they won't call it a good coloring, but we will call it a good coloring so that we don't have to write this big fact statement again. Okay? Now somebody wanted me to explain method 2. Okay? So in method 2, what we will do is we'll count the angles. Okay? Now every angle has, there are two possible vertices, two possibilities for vertices. Either the vertices of a polygon or interior ones. So basically I need to count the number of vertices at the polygon or number of angle sum at the with vertex as a polygon or angle sum with vertex as interior ones. Right? Okay. Now here totally we have 180 triangles, out of which angle sum of polygon is this because of the formula we know n minus 2 into 180. And we have at each vertex, okay, in the interior, the angle sum will be 360 and there are 50 midpoints. So 360 into 50. Simply divide by 180 and you get. Okay. But main idea is take single quantity and count it in two different ways. Okay. This is called double count. So may I erase this? Yes. So I'll give you 2 minutes to do this. Yes. Anybody? Any guess? Okay. Again, here I will use this problem to emphasize the strength of one technique, that creating dummy problem. Okay. So this is a tough problem for us to count because there are various ways you can color, right? So what we can do is we can take a simple dummy of the problem, that we can take a strip of 4 squares, okay? Huh? Simple strip of 1, 2, 3, 4. And now we try to find out how many ways will be there to color this with the same condition that we want odd number of blues. How can we color it with odd number of blues? How many ways are there? Color this with odd number of blues. Okay. Wonderful. Very good. Why 8 beta?
Because if they color for it only one, then you can like 1, 1, 1, 1, or when you see then
Wonderful. What she is saying is right. We need odd number of blues, so blue can be 1. So I can have 1 blue, 3 red, or I can have 3 blues, 1 red. Correct? Pull 1 blue, 3 red. I, that is what you are saying? Or you have different method in mind? Okay. See, we have 1 blue and 3 red, correct? Okay. Then I can select my blue in any of the 4. The same, correct? Okay. So this can be done in 4 ways, correct? My blue can go in first or second or third or fourth, correct? So there are exactly 4 ways to do this. And here my red can go into any of the 4. Correct? So there are 4 ways to do this. Right? Okay? So totally we have 8 ways. Right? So this can be counted in slightly different manner. What I can do is I will count this. This has 2 options, blue or red. This again have 2 options, blue or red. This again have 2 options, blue or red. Now, I will color these 3 freely according to my wish. Okay? Color. And last, I will select wisely so that I will get only odd number of blues. So, how can I select the last one? Suppose my first tree has odd number of blues, already odd blues. Then, okay, let me write here. Odd blues, 3 has odd blues, then 4th one, what color I should give you? Red. Very good. And suppose we have even number of blues, then what color I should give you? Blue. Correct? So last box will give you parity adjustment. Parity means whether odd or even. Okay? So this is for parity adjustment. Okay, parity adjustment, so it has only one way of doing it. Correct? Everybody understood? This is very important thing. Okay, I have used it in many counting problems. Okay, especially when you have to count the number of 10-digit integers such that their sum is even, sum is odd. Same thing you have to do. First few digits you can choose freely. Last digit keep it for piping. Last or last two depends on the question. Okay. So here I am giving last one for parity adjustment. Therefore, I have how many ways will be there? 2 into 2 into 2 into 1. So 8 ways, 2 cubes. Right? Huh? Everybody understood this? Now I have to mimic this technique here. So which part of the board I can color free?
How?
Huh? I want each row should have odd blues. Okay, so which part? Huh?
Like the first one, the first one.
First,
Row and the first one.
first one, first column, you can color blue.
All the others were different. Like they should be decided, and after that, others should be what should do.
Acha, okay. See, I want to mimic this. So in each row, I need last strip as a deciding factor. Correct? I need this strip as a deciding factor. Correct? For every row. I can color this part free for row condition. Correct? So I can ensure every row will have odd number of views. Now I'll go to columns. In columns, I can color first 7 and I will keep this as deciding. Correct? So I can ensure now that all columns are odd blue. Correct? Let's call it odd columns if it has odd number of blues and even columns if it has even number of blues. Okay? Color. So if I color here this 7 cross 7 square, let us call it A. Okay? I can color it freely. Okay? And then what will happen to B and C and D? Let us see. Okay? So we can color square A freely according to anybody's wish, whichever color you want to give, any combination. Okay? Now, once I color A, suppose I color with some random colors. What will happen to B? Does coloring of A fixes colors of B?
Yes.
Yes. Because according to this rule, here it was till 3, but now I have till 7. If I have odd number of blues in my A part, okay, this is my A part, correct? If I have odd number of blues in A part, I should color this 7 by, this is column 7. Column 7 by red. And if I have even number of blues, then I have to color it with blue. Is this clear to everybody? This is very, very important. Huh? Okay, I am ready to repeat. What I'll do, I'll count. If I have odd number of blues here, I should color this red so that the blue will remain odd. But if I have even number of blues here, I will color this blue so that blue will become odd. Okay? So this fixes colors of rectangle B. What can we say about rectangle C? Same. And rectangle C, correct? And what can we say about rectangle? One single square D. Same. And D. Okay, so I will say B, C, and D. Correct? Everybody agree to that? Huh? Yes.
Ma'am, but won't if B and C have colors which will fix D differently, then it will contradict.
Wonderful. I was waiting for somebody to ask this. His doubt is valid. Suppose I fix my square A. Suppose I fix my square A and this particular coloring. Suppose this coloring of A met B such that that B has odd blues and C has even blues. Now B has odd blues, means to maintain this, I need to give D red, correct? Here D should be red and this has even blues, means D should be blue. So this is a big mess or a contradiction. Our method will fail if this happens, right? Wonderful part of the problem is we can prove that such a situation will never arise. So that is my claim. Okay, let me write it this way. Let the number of blue squares in rectangles A, B, C be denoted by small a, small b, small c. So it will be easier for us to write. So claim, we have to claim. Whatever we are feeling, we claim it. What do you mean by claim? This is something I am saying. It's my responsibility to prove it. Okay? Claim that small b and small c have same parity. What do you mean by same parity? Either both are even. That is, either both are even or both are odd. And what do you mean by opposite parity? If one is even, other has to be odd. Okay, everybody understand this terminology? Very good. So B and C have same parity. We have to prove it. So let us see how we are coloring. We are coloring A freely. Okay. So A, what can I say about number of blues in A? Okay. Now there are, what I know about total row or total column, correct? I don't know about partial row or partial column. So let's think of total rows. So let us take A and B together. So A plus B is what? A plus B is first 7 rows, correct? I mean, rectangle A and rectangle B together will be R1, R2, R3 till R7, correct? Complete 7 rows, right? We know in complete row, what is parity of blues? Odd, correct? So I have odd number of blues here. In R2, how many blues are there? Odd. In R7, how many blues are there? Odd. This might be different odd numbers. But we know that number of blues in these rows are all odd numbers, correct? Okay? Followed? So A plus B, what can I say about A plus B? Number of blues in this total area is sum of 7 odd numbers, correct? So A plus B is sum of 7 odd numbers, correct? Followed? Okay. So what can I say about sum of 7 odd numbers? 7 odd numbers, sum is odd. Everybody agree to that? Correct? So what can I say about A plus B is an odd number? Correct? Now everybody understood? I'll repeat again. See, R1, what is this area is my A and this is B. Okay? So what is A plus B? It is sum of first 7 rows, R1 to R7. And we know in each row we have odd number of blues, right? So how many total total sum of blues in A and B? It's sum of these 7 odd numbers, right? Correct? Okay. So what is that? That has to be an odd number. Now let us consider A plus C. What can you say about A plus C?
Also.
A plus C is C. sum of first 7 columns, and each will have or correct check with sum of first 7 columns. Correct? So what can I say here? I will get A plus B is odd number and A plus C is also odd because it is also sum of 7 odd numbers. Correct? Now subtract. B minus C is even. So I'll get B is equal to C plus an even number. So what can I say? A is 1 if B is odd. That implies C is odd. And if B is even, correct? So either both of them are odd or both of them are even. If both are odd, what will be color of my T? T can be colored with red. And if both are even, T can be colored with blue. Correct? So I can color T uniquely. Right? So this gets fixed. Correct? T also gets fixed. Okay? So I have left which part of the board? A part of the board. I can color free. Okay? See, throughout the proof, we have not touched the method how we are going to color A. So any damn coloring of A, for any coloring of A, this proof will work. Correct? Understood? Therefore, total number of good colorings are how many?
49.
Perfect. Now, tell me, was it possible to do a direct something? 2 raised to 49 is such a huge number, right? Okay, so this is a power of mathematics. This is a power of combinatorics. We count without actual count. Okay? See, I don't know much computer, but now you coding and all, you can find out the time required to calculate such a huge number of combinations and all. Okay, for computer also it will be very difficult. But we can do it using combinatorics. That's why combinatorics is such a beautiful art. Okay, anybody needs to copy anything on it? I can erase some part. So I'm trying to give you different techniques. Okay, followed. This is called this is just a counting. I will say. Okay. Now, any part of the board I can clear? Yes.
How did we arrive at 2 raised to 49?
Yes. Let me explain. See, I'm coloring A part 3. A has how many squares?
40.
40. Each square have 2 options. Correct? The way here each square have 2 options. And we have seen that you can color freely. He will color the way he wants, she will color the way she wants. Still, same proof will run. That is why we have to take we have to take general this thing, okay, counting approach rather than specific cases. Okay, is this clear? See, this was also an IMO problem, old IMO problem. See the beauty of the problem. It just uses only basic counting principle, multiplication principle, and only parity. But the difficulty level of the problem is very high. Okay, it's very difficult to come up with such a thought. Okay, now have you heard of pigeonhole principle?
Ma'am.
Okay. Okay. Pigeonhole is very important technique in counting. Okay, commonly known as PHP, pigeonhole principle. What does it say is that suppose I have is n holes. Then there exists. This is a symbol. This symbol is symbol of there exists. This reverse E. There exists at least one hole with more than one pigeon. Okay, I have a habit of writing in short. Okay, to say that. Okay, but everybody is understanding this? So at least one hole with more than one pigeon. Okay? Everybody is comfortable with this? Because suppose no, I say no. Every hole can have at most one pigeon. Then how many pigeons I can accommodate in n holes? Max to max n pigeons. But I have one pigeon who is left out. Correct? Followed? The same principle extended. Suppose we have n holes and kn plus 1 pigeons. Then what can I say? There exists at least
K plus 1.
one hole with k plus 1 pigeons. Because if I say no, suppose if possible, we write this for the set of contradiction. Okay, to prove, okay, this is called method of contradiction. For the set of contradiction or method of contradiction. Method of what is my method of contradiction? That suppose if possible, each hole has less than equal to k pigeons. Okay? Followed? Then total number of pigeons accommodated will be less than equal to kn. Correct? But we want kn plus 1 pigeons. Right? Correct? So which is a contradiction? Followed? So in method of contradiction, we assume the statement which is to be proved wrong and arrive at some contradiction. So this is the short form for that, for the set of contradiction. Okay? So you can freely use this short forms in RMO. Yes, yes. See, in method of contradiction, what we do is whatever is to be proved, we assume it wrong. Okay? And then we arrive at contradiction. And why we got contradiction? Because we assume the statement wrong. This is a general rule. Now for this particular problem, so I assume that if possible, let each hole has less than or equal to k pigeons. Okay? Now totally we have n holes and each will have less than k pigeons, at most k pigeons. So totally there can be at most kn pigeons. But we have kn plus 1 extra pigeon. We have to accommodate so many. Okay? Is it clear to everybody? So let us see few problems based on pigeonhole. First, easiest problems on pigeonholes are number theoretic pigeons. You people know modular arithmetic? Anybody doesn't know modular arithmetic? Okay. What I mean by modular arithmetic is that we say this is no. If I only if n divides a minus b, then simply b is remainder when a is divided by b. Actually, we daily life. Okay? Suppose I started this lecture at suppose 9 o'clock, and suppose I want to trouble the students. I'm in a very bad mood, so I decided to trouble my students. So I continue for 10 hours, okay, non-stop. Okay, what time the lecture will take? 7 p.m. correct? Okay, but ideally it should end at 9 plus 10, 19 hours, correct? Why you say 7 p.m.? See, imagine if we would have not done mod 12, then today's date would have been counted from the beginning when they started counting, okay? Even if they would have started counting in 1st Jan of 2023, what would have been today's hour? It would have been gigantic huge number, right? Okay? So it is nothing, it's just mod 12. We are just after 12, we take remainders when divided by 12. That's all. It's nothing very high-fi. See, remember, maths is all very simple. Because in maths, 2 plus 2 is always 4. It is very well defined, and each and everything has a concrete proof. That is the reason in other theories you will always find that Einstein discarded Newton's theory. Then Stephen Hawking discarded Einstein's theory. In mathematics, no theory ever can be discarded because it is on concrete base of proofs. So you should learn basics, fundamentals very clearly, and your job is done. Okay? So now, so everybody understood what do I mean by what? Okay? Now here, fun part is that we need not write the smallest remainder here. Okay? What I mean by this is that these both give me same remainder when divided by. Okay? So I can say that 7 is congruent to 77 is congruent to 100 whatever 7 mod 10. What I mean by this is all these will give me same remainder. The same remainder when divided by 10. Okay, this is such a simple concept but it has wonderful applications. Why? Because what we do here is this has power of boiling down big fat numbers into smaller numbers. We have seen the example, the time. Okay, I suggest a book to read this. Okay, the mathematical circles were forming dimension. Okay, I'll share the ebook. Okay, with principal sir. From that, divisibility 1 and divisibility 2. These are the chapters you should do for modular algebra. This is such a student-friendly book. Once you take the book in your hand, it is addictive, totally addictive. Okay, chapter 0 is all puzzles. You won't keep book down till you finish all puzzles. Okay, and these two chapters are so student-friendly. You can do it by your own. Okay, and he has given out solutions also behind. Okay, very useful. Okay, by forming symmetry, the mathematical circles by dimension form. Okay, wonderful book. Okay, now this is very good for combi also. Now, so let us do one problem once. Start. T is proved divisible by say 2023 this year. So first I'm doing number periodic physical. Done? Anybody? Any hint? Yes? Okay. What my Pythagorean principle says? If I have n folds, okay, and more than n pigeons, then some two should fall into same pair. Correct? Okay? So I am going to use that. See, I will create more powers of 2 than 2020. Can I get more number of powers of 2? How many powers of 2 are available? Infinite. So, for the sake of, I can take any random, but because I want to write nicely, I will take these or you can take some few more. Okay? For consider these numbers. So, these are my pigeons. Okay? And what are my holes? Consider divisibility of 2023. Okay? So, how many possible remainders are there? What are possible remainders?
0 to
2023 is same as 0. So, I will write till 2020. Right? Hmm? Now, what I want to show? I want to show one of the number gives me remainder 0. It is divisible by 2023 and gives the remainder 0. So, if there exists any 2 raised to a that gives me remainder 0 more 2023, we are done. Correct? That implies 2023 will divide 2 raised to a. Correct? So suppose not. Okay? Then erase this one. So suppose not. So that means all these numbers 2 raised to 1 square till 2 raised to 2024 will give remainder from set, okay, with set 1, 2, so on till 2022, right? Correct? They will give remainder only in this area, no more remainders, right? Now, how many remainders I have? Number of remainders is 2022, and number of pigeons. So these are my modes, and number of pigeons are more than modes. Correct? Strictly more than modes. What is the conclusion?
That more than more than one pigeon, sorry, more than one hole.
One of the
hole
hole
will
has.
have more than one pigeon.
Correct. So some two of them will give me same remainder. Correct? It's simple language. So pigeonhole is very easy principle. You will be amazed. I can create IMO level very tough problem using pigeon. Okay? So never underestimate the strength of pigeon. Okay? So what we say, but this is such a wonderful because this is logical. You don't need very high five mathematics. That's the best part of Olympiad. Some of the problem can be solved with brute force. And that will be your strength. Even if you don't know much theory, you people are smart. That's why I could share a worksheet because I was not knowing the level of the student. But here I decide according to level of student what problems I can do. So we can do some very good level problems. Okay? Now, so here what I can say, this means some two there is, so I will write in little mathematical language. There exists some A and B, okay, between 1 and 2024, okay, followed such that 2 raised to A and 2, or let me write B here, 2 raised to B gives me same remainder. So they are same modulo 24. They give me same remainder. Correct? Okay? Agree? What do you mean by they are giving me same remainder? That means 2 raised to B is some multiple of, oh sorry, one of them. 2 raised to B is some multiple of this, some K plus remainder R, and 2 raised to A is some other multiple, some T plus remainder R. Remainder is same, correct? Followed? So now if I subtract them, what I will get? Oh, sorry. I am dividing by 2023. My bad. Very bad. Sorry. Excuse me. Slip of tongue. I am dividing by 2023. Just, I have to make it. Yeah. So 2023 into A minus T, whatever. Okay, I have taken B greater than A. So naturally K is greater than. So this is a positive integer. Correct? Can I say like this? So can I say that 2023 divides this? Okay, we write this as dividing. Are you aware of this sign?
Yes, ma'am.
Okay. Because you can't see last page. You can't see. If you want, you can come and sit. There is a place. I think there is one place here and one place there. Huh? If you want me to repeat any part, you tell me. Huh? If you want me to repeat any part, I can sit here or I can sit. If you want me to repeat any part, you can tell me. So, I'm saying that this divides this. Like, for example, 5 divides 55. Okay, this is a symbol of that 5 divides 55. Just standing there. Okay, so this divides this. Correct? But can I factorize this? Because A is smaller than B. I have taken one of them will be small. There are two distinct numbers. So you can take anything small. So I can factorize this is 2 raised to A and 2 raised to B minus A minus 1. Correct? Followed? Okay? So, okay, sorry. I gave the question. There is a mod 2 that gives me remainder 1 when divided by the mod 2. I'm very sorry. extremely sorry. This is a blunder. How can the power of 2 be divisible by 2023? Very sorry. Okay. Slip of tongue type of mistake. I mean to say that there exists a power of 2 that gives me remainder 1 when divided by this. So, if there exists 1 with remainder 1, okay, then then we are done. Then we are done. If not, then remainders will be from this set. 0, 1 won't be there. Okay? Follow? Now, rest everything is same. Should I explain from the beginning? I meant that there is a power of 2 that gives me remainder 1 when divided by 2023. Okay? So I collected some extra pigeons. Okay? That holds, my holes are remainders. Correct? If any power gives me remainder 1, we are done. That is what we want to do. But if not, then what I will do, I will take other set of remainders. Now we have extra regions again, so there will be some which will give me same remainder, right? Then that means they will be of this form. So I can subtract, and then I get 2023 will divide their difference. This much is clear to everybody? Now, so I can take it common. Now tell me whether 2023 and 2 raised to 8, do they have anything in common?
No.
They are co-prime. So can any part of this cancel with this?
No.
So that implies that 2023 must divide 2 raised to 3 minus a minus 1.
Yes.
Correct? Okay. What do you mean by this? That means 2 raised to b minus a gives me remainder 1 when divided by 20. Follow? Is that clear? So pigeonhole is a very strong thing. We'll see one more problem by pigeonhole. See, only drawback of pigeonhole is that doesn't tell you which exactly power it will going to be. That will give you remainder. It is an indirect technique. It proves the result, but doesn't tell you specification of which exactly power is going to give you power. Understood? That's the only drawback. Okay, done. May I erase? Any part he has not understood? You want me to explain anything? Which one? You tell.
Ma'am, he didn't understand where to realize.
Check to
Co-prime.
Yeah, see beta. This number divides this. Okay? Now, does 2023 and 2 have anything in common? What do you mean that this is an integer? That means this denominator perfectly divides. It gets cancelled with 2. But these two doesn't have anything in common. That means 2023 must cancel this one. Right? Correct? So it must divide this. Understood? Because these two doesn't have anything in common. Okay? Otherwise, if they would have something in common, I would have cancelled that. But can I cancel any part of 2023 part? Because these are just 2's. This is an odd number. It doesn't have factor 2. Understood? May I? Yeah, I can erase this. be the set of 9 integers. M be the set of 9 integers with prime factors of these integers less than or equal to 6. Means none of the integers have prime factor greater than 6. Okay, so you can say strictly less than 6 because 6 is not prime. So only possible prime factors are
2, 3, 5.
2, 3. Correct? Okay. Prove that there exists some two integers a and b in M such that a into b is a perfect square. Okay, again I repeat the question. M is set of 9 integers. Okay, so let me write M as some a1, a2, a9. Okay, and such that these has only possible prime factors 2, 3, 5. Now it may happen that one of the number has only 2's, one of the number has combination of 2 and 5, other number have combination of 2 and 3, any combination, but no other kind. We have to prove that there will be some two numbers whose product is a perfect square. I can find some two. Okay? Follow? Let's break this problem. Was it a tougher problem? How many of you found it little tough? Okay. Then probably we'll do this little later. Let us do one easy.
All are distinct.
Yeah, 9 distinct integers. In a set, there will be always distinct. In a set, we don't repeat. Okay? What do you mean by a set 1, 1, 2, 3? It's saying this is just this. Set is a statement that 1 belongs to this set. There's no point in saying 1 belongs to this set. Again, 1 belongs to this set. Huh? Okay? Follow? So, if you want to repeat elements of set, it is called multi-sets. Okay? And you need to specify. Unless specify, you assume sets are simple sets. Okay. Then, probably, I'll do some easy stuff. Yeah. Consider a set of 6 people. Okay, any 6 people. Okay? Among any two, they are either they know each other or they doesn't know each other. Okay? Follow? So I will say it's a mutual relation. What do you mean by mutual relation? See, basically, Dr. Jan Ghadigaonkar, he should not know who is Komal Ghadigaonkar, correct? But Komal Ghadigaonkar knows who is Jan, right? But for this problem, we assume that if Komal Ghadigaonkar knows who is Jan Ghadigaonkar sir will also know that someone Komal Ghadigaonkar exists. Okay? Followed? In real life, it is not like that. But we will assume it. We'll assume that if A knows B, that implies we must know it. Okay, knowing is mutual. Similarly, not knowing is also mutual. Hmm? Okay. So we have 6 people. So among these pairs, how many pairs will be there out of 6 people? Total possible pairs.
62.
62 possible combinations, possible pairs. Okay. Among this, every pair will have either both of them know each other or both of them doesn't know each other. Everybody understood this?
Yes.
Now, so we try to prove that. Prove that there always exist 3 who mutually know each other or 3 who are mutually unknown. Means what I'll explain. Don't worry. Means there will exist some 3 A, B and C. Such that A and B know each other, A and C know each other, and B and C. Or if you write here, you are unable to see it. Huh? Okay, I'll use upper part. But you need to communicate freely. Huh? Okay. Or in this case, what will happen? A, B, and C, they don't know each other. These two don't know each other, and these two don't. Okay? Everybody understand? Huh? Is this clear to everybody? Huh? Now, so this will happen for any 6 people. Any 6 people throughout the globe. Okay? Any 6 people you pick up of your choice. This will be always there. Either there will be 3 who mutually know each other, A knows B, AB know each other, BC know each other, AC know each other. Or there will be 3 such that AB doesn't know each other, AC doesn't know each other, and BC doesn't know each other. Is this much clear? Huh? This is what we are going to prove. Okay, everybody understood the problem? I'll give you 2 minutes to think about it. Okay? Tell me about first 2 questions. Everybody understood first 2 questions? What was the difficult? Anybody? How many of you found the first question difficult? The second question. So everybody understood second question also. Wonderful. Third, I don't understand. Modular arithmetic. Okay, I'll have one technical. Okay. Yeah. Now here, so consider a set of 6 people. I need to prove that 3 mutually know each other, 3 who doesn't know each other. Okay? So what I will do is, if they know each other, I will denote the people by points. Okay? Let's denote the people by points and the relation between them by segments. Okay? And if A knows B, we will color it with blue then we will color it with red. Okay? Followed? Huh? Okay? So what we have now? We have 6 points. We have 6 points. A, B, C, D, E, F. Okay? And between any 2 points, between, can I use short form for between any 2 points, there is either yellow segment or a red segment, correct? Because between any pair of Bacha, I appreciate you are discussing something. See, between any pair of people, either they know each other or they doesn't know each other. There is no third option, right? So either I have a red segment or a yellow segment. Everybody agree this much? Now, let us consider segments coming out from point F. How many segments come out from point F? 5 segments. There are 5 segments from point F, and we have 2 colors. These 5 segments will be colored with 2 colors. Yellow or red. These are my poles and these are my pigeons. My segments are my pigeons. Okay? So I have phi is equal to 2 times 2 plus 1. Okay? So I claim that there are at least 3 segments which are of same color. Okay? I claim that. Because I said no. Suppose there are only 2 segments of the any color. If not, then I may have 2 yellow plus 2 red. I can color only 4 segments. But how many segments I need to color? 5. Correct? So what we need is, we need at least 3 segments of the same color. Okay? So what I will do is, right now I will assume these 3 segments are, which color you want? Yellow. Red. What? Red. Okay. Now, I can, this is my case 1. Case 2 is yellow. I'll write that. So first case is, suppose 3 segments are red. Okay. Now, you can take the chair this side. So, what I'll do is, or you can keep it there also. Anywhere where you feel. Now, so now what we can do is, we take some 3 segments red. Even if there are some other segments red, I can give a similar proof. But right now you assume these 3 segments red. So let FA, FC and FD be red. Let FB and FC be red. What I mean by this? That means these 2 doesn't know each other, and these 2 doesn't know each other, and these 2 doesn't know each other. What I want to prove? I want to prove that there will be 3 you mutually doesn't know each as a yellow. Okay? So, so I assume that, see, same proof will run, exactly similar proof will run if some other three segments are red. Okay? So FA, FB, FC are red. So now again, if AB is red, then what will happen? If AB, AC, sorry, what I am writing and what I have colored is different. Sorry, my bad. Huh? FC and FT. I'm little absent-minded. Sorry. FA, FC, and FD be red. Okay. Then if AC is red, okay. If this is red, then I'll get triangle. FAC red, correct? Alright. Here. And if now, if CD is red, then triangle FCD will be red triangle. Can you see? If this is red, then FCD is a red triangle, correct? And if AD is red, then triangle FAD is a red triangle, correct? Everybody understood this much? Huh? Okay. So what I am saying, first I assume that some three of them are red. Okay. And then if I join these edges, okay, they can be also red colored. If any one of these is red, I'll get a red triangle. If AC is red, then AFC is a red triangle. If CD is red, then CFD is a red triangle. And if AD is red, then AFD is a red triangle. This much is clear? Now, if not, means if my what are red, FA, FC, and FDR red, and I'm claiming that suppose these are not red, AC is not red, that means it will be yellow. If none of them is red, means these three will be yellow, correct? If none of them is red, then these three will be yellow, correct? If not, if none of them is red, if none of AD, AC, CD and AD is red, that means they are yellow. So we'll get a yellow triangle. Triangle ACD is a yellow triangle. What I wanted to prove that there exists either a red triangle or a yellow triangle. So if any of, see, if AC can be either red or yellow. If it is red, I'll get a red triangle. Otherwise, it is yellow. CD can be red or yellow. If it is red, I'll get a red triangle. Otherwise, I'll get it is yellow. AD can be red or yellow. If it is red, I'll get a red triangle. If not, I'll get a, it is yellow and I'll get a yellow. Correct? So either I will get a red triangle or I will get a yellow. Understood? Huh? Or it is little tough for you to understand? How many of you are finding this problem tough? Everybody understood? Very good. So this is a technique called coloring. Okay? This is called coloring or coloring groups, and in IMO nowadays they are asking more of coloring groups. Okay? More and more of coloring groups. So, and chessboard problems, especially in recent IMOs, you will find more coloring and chessboard problems. Okay, so this particular problem is very famous by the name of, yes, you know, monochromatic triangle. Mono stands for single, chromatic is color. Mono stands for single and chromatic is for color. So monochromatic triangle means what? Triangle of single color. And this 6 is the smallest number for which I can guarantee that there will be a, if I color the segments by two colors, I will get a monochromatic. But suppose I consider 3 people only, then I can have such a relation. There is no monochromatic triangle. Suppose I consider only 4 people, then I can have relation like this, and these two know each other. So do I have a triangle here? What about this yellow triangle? That is not a triangle because that is not between two people. Understood? Any doubt? Please ask. There are only two situations when you don't have that. Either you know everything or you have not understood it. Okay, so I am eager to know the doubts. Okay, now 5 people. Okay, okay, so 6 is the smallest number for which this property holds. So 6 is the smallest number for which this property holds that there exists a monochromatic pattern. Okay, if I color the segments by two colors. Now, this leads to a wonderful theory ahead called Ramsey theory. Now, it is a very advanced theory. Okay, we need not worry about it right now. I just give you the idea. Okay, so entire Ramsey theory is based on only vision.
It's like points.
Yes, wonderful. You know it. Okay, I'm yes. Okay, so she knows. Very good. I'm very happy. How do you prove that? Think of it. Huh? Possible. I can teach you to do that. That is also a counting problem. If you are interested, see, actually, in 6 people, we can show that there exist 2 monochromatic patterns. Okay? But looking at the reaction of people, I think I'm going a bit overboard here. Okay? So let's come to some counting problems then. See, it's your choice. If you feel this techniques are little high level, then I'll tune down. Okay? I can go to yeah. You have relations between all of them. Everybody. See, there are ages between any two. There are, have you, I don't think everybody has understood the proof. See, here I have drawn these 3, but we call it without loss of totality because you same proof we can give if we draw any other way. Understood? Huh? Okay? Okay. What I will do is I'll give you one easy problem. Chessboard problem? Chessboard? Yes.
How did we solve that relation?
I'll explain. I'll give them another problem analysis. I hope everybody has copied this problem. Okay. This is purely number theory. Anybody wants me to do it or I'm combinatorial number theory?
What do you mean by loss of generality?
I have to explain. Just wait. That thing I wanted to explain with the help of this problem. See, yeah. But let me give one problem because people are getting more. Okay. Again, I have 8 cross 8 chess. Now I have roots. Okay, what do you mean by roots? Elephant. How does root travel?
Straight line.
Straight line, either in a row or in a column. Okay, find the number of ways. First question is find the number of ways of placing 8 rooks in friendly manner. What do you mean by friendly manner? Means
They do not attack.
yes, no two rooks will attack each other. Okay? And how many maximum you can place? That also you think and tell. That is very obvious question. 8. You can't place more than 8. Why?
Yes.
PHP. Wonderful. I'm liking it. He said PHP because if there are more than 2 rooks, more than 8 rooks, some 2 of them will share a row so they can attack. Wonderful. Okay. So find this. Meanwhile, I'll explain this. See, what I mean by without loss of generality. See, in this proof, though I have taken the specific edges, I have not used property of the specific edges to prove the problem. I have taken the specific edges so that it will be easier for me to write the proof. But I have not used any special property of these. Right? So same proof will run if I, instead of FA, if I would have taken FB. Correct? Same proof I can run for FB also. Right? Any 3 edges. Instead of red, if I choose yellow color, some 3 are yellow. Still similar proof can be run. Correct? I just need to replace this red by yellow and yellow by red. Right? Such a proof while writing we write without loss of generality. What do we mean by without loss of generality? Though we are assuming that this thing are red, we are not losing any generality. Okay? Followed? Understood? But you have to be very careful while assuming things. Okay? It should run parallel in all cases, then and then only you can assume. Followed? Okay? So you understood meaning of without loss of generality? Okay? Now, okay. Yeah. So may I erase this? Anybody has any doubt? Yes. And it proceed. Now, what do you want to do? Yes. I'll give you last. Huh? Yes, wonderful. Very good. You're close by. You are very close. I don't want anybody to give away answer. It loses the fun. You know, everybody should get a fair chance to, enjoy that they themselves have solved the problem. Wonderful, very good. What is your name? Harry. What I would suggest to prove there exists two modes. Monochromatic angles and dichromatic angles. Any angle can be monochromatic, elevated, or it will be dichromatic. What do you mean by dichromatic? It's difficult how to it is easy to how how many monochromatic angles will be like dichromatic and less you can do this because for everyone is there is at least three monochromatic angles. Okay, so you have to take the combinatorics. Okay, that's example. How many unique dichromatic angles are what? So there is three red, three or two blue, or four red, one blue, or all five. Okay. So monochromatic angles. Okay. Using that, you will get the limit on. Okay. So this is another way. Using that, you can. Okay. You will have yes. Coming to this problem. Okay. Coming to this problem, what we have. What we have is number of ways of placing 8 groups. Okay. Now first group. Yes, very good. 8 factorial. Huh?
8 factorial
Square. And what is your argument for 8 factorial? Yes. For first group, group number 1. How many ways are there? 64 ways are there. So suppose I place it here. R1 I place it here. What will happen? I can't place my second row in these two. Correct? So one row and one column is got cancelled. So this is as good as, suppose I shift this here. This row here and this column here. This is as good as believing this part. Correct? Follow? Imagine this row and this column I have shifted to last and this row I have shifted down. Imagine I have shifted this here and shifted this down. Correct? So I have this part which has this 7 cross 7. So for root, second root I have 7 square is equal to 49 square level. Okay? Or if you can't see this, in each row one square is cancelled. Correct? So there are 7 square left now. And one total row is cancelled. So we have 7 rows with 7 square each. Okay? Now, so now let me place my second row somewhere here. Suppose now I am cancelling one more pair of one more row and one more column. So basically I am cancelling second row and second column. How many will be left for my root 3? 6 square. Then for root 4, root 5. there will be a unit place there. So total number will be total number of placements will be, or arrangement will be, I have 1 square, 2 square till 8 square, which is nothing but 8 factorial whole square. Correct? Everybody? Huh? This much is clear? Now, let me give a similar problem. You have
Recurrence relation.
5 currents relation. Just give me, yeah, this is okay. Yeah. Let me explain his method also. He has done by recurrence relation. What I mean by recurrence relation? Okay. See, if I say an be the number of ways of placing n roots on a n cross n chessboard. Okay. Suppose n being this. Now, so this is my n. So when I place first row, how many possibilities are there for placement of first row? On n cross n chessboard. N square. N square. Correct? And then what will happen? I will delete one row and one column. So I'm left with correct? Okay? Follow? So a yeah. So I can say that a n is equal to n square times a n minus 1. Correct? Because placing one row, I have there is no need for this. Sorry, I went from solving. A n is equal to n square times a n minus 1. Can I say like this? Huh? Such a kind of relation is called recurrence relation. Okay? So using this, I can go on backward and calculate, or I can start from what is A1? Placing one row on 1 cross 1, which is 1. Then A2 will be 2 square into A1, like that. See, A1 will be 1. What is A2? That is 2 square into A1, which is 2 square. Correct? What is A3? 3 square into A2. That is 3 square into 2 square. Correct? And so on. You go on. Correct? So you will get An is equal to n square into An minus 1, and An minus 1 you will get product of all square previous. So that is okay. Is that clear to everybody? This is also very powerful thing. Okay, recurrence relation is also a very powerful thing. Okay, followed. So I think there will be a break. So before break, I would like to give 2 problems. One problem is on for chessboard. Okay. So first problem is 15 rooks are placed on a chessboard in a friendly manner. What do you mean by friendly manner? No two will attack. Okay. Now, then each rook is changed according to what it is called. Course is called right. Change according to on night move. two units and then yeah, okay, in any direction. Right? Now prove that now all 15 are not in friendly position. Means what? I have 15 rooks and initially they are in some friendly position. Okay? And now I will change each rook in a knight's move. Now I need to prove that there are all 15 cannot be in friendly position. Means there will be some at least some two rooks. Which will? Yes.
And what is the size of this chessboard?
15 cross. Okay. Yeah, sorry, my bad. A 15 cross. Okay. Followed? Sorry, being little absent because I'm creating. I'm not planned for this lecture. According to your response, I'm finding the problems in my mind. So there might be some mistakes. Please, you will have to bear with me. I'm a little absent-minded person. Okay? Yeah. Okay, everybody understood this question? Now, there is a very simple. Suppose I have a staircase with whatever 1 to 10. Okay? I have a staircase with 1 to 10, and a child can jump single stair at a time or 2 steps at a time. Child can jump 1 step at a time or 2 steps at a time. Okay? And child has to go from 0 to 10. So you need to count how many different ways child can go. Okay? So it can take 1 step or total 1 step or in between 2 steps, or it can take all 2 steps, or it can do various combinations of 2 steps, 1 steps. Okay? Hold on. So I need to count the number of ways. Okay? Hold on. Is that clear? Once again I will repeat. We have a staircase from 0 to 10. Okay? The child either can go one step or he can jump 2 steps. Okay? So we need to find number of various ways it can. Is it a time for break? Stop. Okay. So I'll stop here and we'll meet up. So these two problems are given, so you can work on it during your introduction. Yes. In first question, initially 15 rooks are already placed on the board in friendly manner. Means no two rooks in any row or no two rooks in common column. And then uh, every rook moves along a knight's move. Okay? And after they change along a knight's move, we have to show that some two rooks will be in hostile. That means they can attack each other. That means some two rooks are in same row. Anyone counts number out of 10 you are counting one.
मैडम टी ब्रेक सर्टिफिकेट एक मिस किया तो 90 हो गया दर्शन